Hi everyone, my name is Fahd Husain and I'm the Director of AI Research at InCharge Software. In today's talk, I'll be presenting our latest work, a multi-scale visual analytics approach for exploring biomedical knowledge. The motivation for this talk is well known today. The scale of scientific knowledge is overwhelming, with over 50 million peer-reviewed articles in existence and about 1.5 million more added yearly. It is difficult and time-consuming, if not impossible, to continuously review this ever-growing body of literature and synthesize new knowledge. Of course, all this is only exacerbated by crises like the COVID-19 pandemic. This paper will focus on the field of biomedicine, where such difficulties arise around use cases like drug discovery. As many biological processes are inherently network phenomena, researchers will often work with very large knowledge graphs extracted from scientific literature. They'll look to identify subgraphs and pathways for explaining and predicting interactions, and isolate candidates for downstream clinical work. However, such workflows are impeded by sheer size and dense connectivity of the knowledge graphs involved, making it time-consuming to develop and validate new hypotheses. Typically, graph visualization approaches are either static overviews of the graph or interactive views of small subgraphs. Yet the multi-scale nature of biological networks means that a researcher must continuously and interactively engage with both local and global graph structures. Similar network visualizations are also sometimes used for displaying knowledge corpora, but clustering is a more common approach, with documents cast as points in a 2D topology. Against this backdrop, we developed a multi-scale visual analytics approach to enable the interactive exploration and analysis of biological graphs linked to scientific corpora. This work was done under DARPA's Automated Scientific Knowledge Extraction, or ASCII, program. We followed a user-centric design process, engaging with biologists and biomedical researchers from the onset. From these interactions, we distilled three core design goals. First, to provide scalable and interactive visualizations of biological graphs, irrespective of whether such graphs had a dozen nodes or tens of thousands. Second, we had to enable local analysis coordinated with global context, allowing researchers to work in focused subgraphs without losing higher-level awareness. And finally, to promote knowledge synthesis and discovery, we had to ensure that graph analysis could be contextualized with a backing scientific corpus. Our prototype is divided into two spaces, the graph space and the knowledge space. The graph space is shown here with a biological graph. This is a global view of the knowledge graph on the left and a local, more focused view on the right. As we'll see, these are coordinated in interesting ways. As the default view, the global view provides high-level graph overviews. The biological graph data here is provided by our collaborators, with these graphs being assembled from causal statements extracted from scientific literature and then organized in a background biomedical ontology. We use a hierarchical circle packing layout to arrange biological agents in the nested concepts of the reference ontology. Each ontological group is rendered as rings around its children. To avoid displaying hundreds of thousands of edges, we also apply edge bundling techniques, where edges with multiple nodes, grounded to the same ontological category, are bundled into hyperedges. Hyperedges are also wrapped around ontological rings to avoid edge clutter between groups, and hyperedge brightness corresponds to the number of bundled statements. Semantic zooming progressively discloses the nested categories of the ontology as the researcher dives deeply into an ontological branch. This view also allows researchers to interrogate biological graphs by using multi-faceted queries. Query results are displayed on the global view using contrast-based highlighting, as we'll see, with results foregrounded and the rest of the graph faded out. To aid researchers in sense-making, we supplement the global view with the local view. The local view is a sandbox where search results from the global view can be iteratively added for further inspection. Edges are visually encoded based on the implied polarity of the regulation type, curation state, and directionality, blue for positive, red for negative, and gray for unknown. Other graph attributes like human verification are encoded with filled circles. Researchers can also explore link suggestions for nodes, node metadata, and surface underlying textual evidence for each edge in the side panel, and then follow these links back to the original documents. Let us now see some of these ideas in action. Here, the user interactively zooms into a knowledge graph for breast cancer, with over 1,000 nodes and 5,000 edges. Concept rings in blue contain biological agents in orange. Queries on various graph attributes are possible and are made available via the search bar. Here, a query is done for a specific edge type, and query results are foregrounded. The rest of the graph that did not match the query is backgrounded. Semantic zoom is able to reveal the biological agents that were part of the query result, as well as the nested branches of concepts in the ontology that contain those agents. This provides a high-level overview for the user. Next, the user selects the COVID-19 graph from the list of available models. With over 40,000 nodes and 350,000 edges, this is a very dense network. The user is able to utilize their prior knowledge and use a relevant document identifier to seed the query. Results highlight the interaction statements extracted from the document in question, as well as the related concepts. These can be pulled out into the local subgraph. Interacting with a node here surfaces the neighborhood of that node and highlights the connectivity of that node in the global view as well. Edges can be investigated for evidence and traced back to source and related documents. Here, the user expands their query with another document identifier. Both the global and the local views are updated in terms of highlighting. Edge interactions work the same way. Path connections into the node are highlighted, and the global context is also made available. The second space of the prototype is the knowledge space, and this provides interactive search and access of the scientific corpus. This space is divided between the cards view and a clusters view. The card space view uses a tabular layout with chunked information for each document displayed as a card. Rich query capabilities are enabled via API over attributes extracted by our collaborators, including text, metadata, and artifacts. This view encourages scannability, but suffers in terms of scalability. The clusters view provides a more scalable perspective on the overall scientific corpus. Using hierarchical clustering on document vectors, this view organizes similar documents by color into nested clusters, where each cluster at each level is marked with a polygon boundary. Clusters at the finest level of the hierarchy have the highest opacity, whereas high-level or coarse cluster boundaries are faded out. This still remains an experimental space undergoing current development. More work needs to be done to smooth out the visual encodings and enable interactive search and recommendation. Here's a brief demo of the knowledge space. As described, the user is able to search for keywords and artifact type and then scan previews as well as document metadata. They can also open the cluster view and interactively explore the corpus topology for related documents in real time. They can also drill down as needed. Overall, the user can use the knowledge view to discover relevant documents for their work and then use these to seed analysis in the graph space. A number of threads remain in terms of future research. First, graph navigation and search can be improved significantly in both the global view by better overviews and the local view for more contextualized neighborhood suggestions. Of particular interest to us are graph embeddings, as converting graph structure into vector representations stands to enable downstream analytic tasks such as subgraph similarity, path ranking, and link prediction. Similarly, the clusters in the knowledge view can use visual refinement, and other semantic layers can be incorporated. Overall, the system is extensible to other workflows with hierarchical graphs linked to documents. Not only then could this apply to a range of biomedical cases, we believe it could aid in knowledge discovery across different domains. To learn more, please refer to our paper or feel free to reach out via this email. Many thanks for your attention.